Welcome to This Explainer. I am absolutely thrilled you're joining us today because we're going to set the record straight on a topic you literally hear about all the time. We are going to completely dismantle one of the most famous biological myths of our era and rebuild it using pure, fascinating science. We are rethinking dopamine.
Okay, let's dive into this because pop culture has totally skewed our understanding of this chemical. You hear it everywhere, right? People say every like on social media, every swipe on a dating app, or grabbing that massive iced coffee is giving you a hit of dopamine. We just naturally assume it equals pleasure. But what if everything you thought you knew about dopamine was completely wrong?
You've probably heard it called exactly this, the pleasure molecule. Well, we are going to shatter that illusion right off the bat. The actual neuroscience tells a completely different and, frankly, a far more beautiful story. Dopamine is not about pleasure at all. It is not a little squirt of happiness your brain hands out for a job well done. So if it's not giving us that feeling of joy, what exactly is it doing?
Dopamine is actually the brain's signal for the gap between expectation and reality. It's a teaching signal for surprise. Think of dopamine not as a reward, but like a tiny prophet living inside your head. And this prophet basically has one single vital job: to be surprised and to broadcast that surprise so loudly that the rest of your brain rewires itself to be less surprised next time. To see how this massive paradigm shift actually happened, we have to travel back to the 1990s.
Section 1. The surprise signal. Wolfram Schultz's breakthrough.
Now, what's really interesting about this slide is the story behind it. In the 90s, researcher Wolfram Schultz was recording individual dopamine neurons in monkeys as they learned to associate a cue. Imagine a monkey learning that a sudden light means a drop of sweet juice is coming. Initially, boom, dopamine spiked when the juice arrived. It was an unexpected reward. But as the monkeys learned the pattern, that dopamine burst actually migrated backward in time, moving away from the juice and onto the light cue. Once the reward was perfectly predicted, the juice itself caused a completely flat response. Zero dopamine. And if the expected juice failed to appear, the dopamine levels actually dipped below baseline. So the crucial point here is that Schultz and his team realized they weren't looking at a pleasure meter at all. They were looking at a reward prediction error. It's the literal mathematical difference between what you expected and what you actually got. Dopamine is simply your brain's error correction voice saying, hold on, the world just surprised you, update your model. And this leads us to something truly mind-blowing that bridges the gap between primate biology and modern technology. Section 2, the algorithm of desire. Biology meets AI. Around the exact same time Schultz was monitoring monkey brains, computer scientists were developing something called temporal-difference learning to teach machines how to learn. It's the algorithmic backbone of reinforcement learning. And here is the incredible convergence, the absolute awe of the subject. Schultz's biological dopamine neurons were computing the exact same mathematical quantity as those AI algorithms. Human brains and silicon machine learning models are quite literally running the exact same math to figure out their environments. So if dopamine is just a cold algorithm for updating predictions, where in the world did the whole pleasure myth come from in the first place? Well, it comes from confusing two entirely dissociable processes in the brain: wanting versus liking. Dopamine drives the wanting. It's the craving that makes you reach for that powdered donut in the break room. But the actual hedonic pleasure, the liking you feel while eating it, that's driven by entirely different systems in the brain utilizing opioids and endocannabinoids. And this stark dynamic perfectly explains the tragic cycle of addiction. Addictive drugs chemically hijack the dopamine system. They artificially create massive prediction errors, essentially telling the brain, wow, this was way better than expected, over and over again. The wanting grows monstrous, while the actual liking, the true, genuine enjoyment, fades away. The brain is taught to pursue the substance with escalating hunger, even as the pleasure is completely gone. But we also have to look at the other end of the spectrum. We need to see what happens when the signal fades entirely. Section 3, the void, when the signal fades. Ask yourself, what happens when the surprise signal just goes quiet? Imagine a stark, low-energy reality drained entirely of its incentive color, a world where nothing exerts a magnetic pull on you, where absolutely no goal feels worth the effort. In neuroscience, this is known as anhedonia. It's a core feature of depression, and it is fundamentally a disorder of the reward circuitry. The science shows us that in depressed individuals, a brain area called the ventral striatum under-responds to positive events. The dopamine teaching signal essentially dims. Without that crucial signal shouting, hey, this is surprisingly good, the brain's machinery literally forgets what's worth pursuing. Which brings us to the cutting-edge frontier of modern research and how science is attempting to switch this broken reward machinery back on. Section 4, the psychedelic hypothesis, rewiring the reward system. There is a fascinating new frontier in neuroscience right now. Think about it like this. A depressed brain has essentially stopped being surprised by good things. Psychedelics may actually teach it to be surprised again. In a really striking preclinical study, researchers found that a single dose of psilocybin reversed anhedonic behavior in chronically stressed mice. It completely restored their drive to pursue a sweet reward. And this brilliantly illustrates that this isn't just about flooding the brain with happy chemicals. Psilocybin actually strengthened excitatory synapses, reopening a vital window of synaptic plasticity. Amazingly, the reward-restoring action persisted even when the classic psychedelic trip receptor, the 5-HT2A receptor, was chemically blocked. So the psychedelics are essentially allowing a stuck, under-responsive system to finally relearn. Now, hold on. We need to be incredibly clear about the science here, so let's carefully review the honest cautions from the source material. This explainer is covering early promising research, but it is definitely not a silver bullet. These are preclinical rodent data, not settled clinical facts for humans, and the exact mechanisms are actively debated by scientists. Also remember that dopamine has many other essential functions, like movement and working memory, so reducing it to just one thing is always a mistake. And of course, this is absolutely not medical advice. These are controlled substances, and anhedonia requires professional medical care. But the core takeaway of this entire paradigm shift is just deeply profound. Motivation is not a mood, but a computation. Once we strip away the whole pleasure myth, we see our entire drive rests on this fragile, beautiful signal of surprise. So if your daily motivations are essentially just your brain crunching predictionaries, what are you going to teach your brain to be surprised by tomorrow? Thanks so much for joining me for this explainer.